Hello, this is Mrs. Scarpel, and this is part 1 for Lesson 9 of Unit 2, Lining Up Quadratics. In this lesson, our focus is going to be on finding patterns to efficiently graph quadratic functions from factored form. So in our previous lessons, we've been factoring from standard form. Today, we're going to start working with how do we graph from factored form. So what features of a parabola are highlighted in factored form? How can we use those features to graph a quadratic function? And how does the factored form of a quadratic equation relate to graphing a parabola? So to begin with, in class, we actually used our calculators to graph the equation. And so you will see here the image of the graph from the graphing calculator. And then we identified the X-Intercepts, the line of symmetry, the vertex, and the Y-Intercept, and then we graphed it again by hand on our graph in our notes. So for the equation y equals x minus 1, x plus 3, this is our graph. And if we look at identifying the X-Intercepts, X-Intercepts are where we cross the x-axis. So we have one x-intercept at -3 or -3, 0. And we have the other x-intercept at 1 or 1, 0. The line of symmetry is that line that divides our parabola into two symmetrical parts. That line goes through the vertex of our parabola, and it's halfway between our midpoints. So if we just look at this, we're going to find our line of symmetry at x equals -1. To remind you how we can find that mathematically, we would take the values of our x-intercepts, add them together, and divide by 2. So -3 plus 1 is -2, and -2 divided by 2 is -1. Now remember, I said the vertex is located on this line of symmetry. So that means our vertex is going to have the same x value as our line of symmetry. And if we look at our graph, this appears to be down 1, 2, 3, 4 units. So -1, -4. Now just to clarify how we could find this mathematically, we want to plug the value of the line of symmetry for x in the equation and simplify. So if I just check by plugging into our equation, which was x minus 1 times x plus 3, we're going to have -1 minus 1 times -1 plus 3. So -1 subtract 1 is -2. -1 plus 3 is +2. When I multiply those together, I get the -4 that we have for the y value of our vertex. The y-intercept is where the graph is going to cross the y-axis. So in this graph, it is down 3 units. The x value is 0. The y value is -3. And to find the y-intercept, mathematically, plug 0 in for x in the equation and simplify. So if we check that we are in fact correct, that the y-intercept is at -3, we're going to have 0 minus 1 times 0 plus 3. Well, 0 subtract 1 is -1, 0 plus 3 is 3, -1 times 3 is -3, which is what we have for the y value of our y-intercept. So let's go ahead and graph this again using this information. We have x-intercept at -3 and at 1. We have a line of symmetry that passes through x equal to -1. Our vertex is on that line of symmetry at -4. And we have a y-intercept at 0, -3. And because a parabola is symmetrical, I could plot another point at 2, -3. And then we can graph our parabola, keeping in mind that parabolas are curves, so it's not a sharp V at the bottom. You want to make sure that it is rounded as you pass through the vertex. With example 2, again, we graphed it initially on our calculator, so this graph in the upper right corner of your screen is the graph that was on the calculator. We identified the x-intercepts as being located at 2, 3, 4, 5, and 6. So 2, 0, and 6, 0. The line of symmetry should be halfway in between. So that's located at 2, 3, 4. X equals 4, and we can check that mathematically by doing 2 plus 6 divided by 2 is 8, divided by 2 is 4. We know that the x value of the vertex should also be 4. And if we look at this graph, it looks like we are down 8. So that would be a -8. But let's just check mathematically. So y equals, substitute 4 in for the x, so we have 2 times 4 subtract 2 times 4 subtract 6. That leaves us with 2 times -2, 2 times +2 times -2. So 2 times 2 is 4, times -2 is -8. We can't see the y-intercept on this graph, so we take the time to plug in 0 for x, so 2 times 0 minus 2 times 0 minus 6, and we have 2 times 0 minus 2 is -2, 0 minus 6 is -6, 2 times -2 is -4, times -6 gives us a positive 24. So our y-intercept is located at 0, 24, and that's why we don't see it on our graph. But we can use the other points to graph. We have an intercept at 2, 0, 3, 4, 5, 6, 0. We have our line of symmetry at 4. We have our vertex at 4, -8. 1, 2, 3, 4, 5, 6, 7, 8. And our y-intercept, I don't have enough on my graph to graph that either. and we can graph our parabola. See if I can do this better. Through the 3 points that we do have. Now this 2 that we have in front is the stretch, so this graph should look narrower than our last graph did because it was stretched. If we look at number 3, again I have the graph in the corner here of negative x times x plus 4. The intercepts are located at negative 4, 0 and 0, 0. The line of symmetry appears to be at negative 2. But let's go ahead and double check. So negative 4 plus 0 divided by 2 is negative 4 divided by 2 is the negative 2 that it appeared to be on the graph. So we have x equals negative 2 for the line of symmetry. The vertex will have an x value of negative 2. On this graph, it looks to be up 4. So let's just check with some math here. So we're going to have a negative 2 because we're plugging in negative 2 for x times negative 2 plus 4. Well, the negative 2 is like saying the opposite of negative 2, which is positive 2. Negative 2 plus 4 is a positive 2, and 2 times 2 is 4. So we have our vertex up 4. We have the 2 x-intercepts. The y-intercept on the graph happens to match one of the x-intercepts. It's at 0, 0. And again, we can check this. Y equals negative 0 times 0 plus 4. Well, negative 0 is just 0. 0 plus 4 is 4, and 0 times 4 is 0. So using our information, we can plot our x-intercepts at negative 4 and 0. We can show that the line of symmetry is at x equals negative 2. We can plot the vertex on that line of symmetry at negative 2, 4. Again, that one y-intercept matched an x-intercept. And we can graph our parabola through these points. And it's reflected down or open downward because of the negative that is in front. So what are some of the things we saw? To find the line of symmetry of the parabola, we add the x-intercepts and divide by 2. To find the vertex of the parabola, plug the value of the line of symmetry. For x, and simplify. To find the x-intercepts of the parabola, I'm just going to go back a couple screens here. You notice on number 2, our x-intercepts were at 2, 0, and 6, 0. If you look at our equation in factored form, it's the opposite of the constants inside our factors. So instead of negative 2, we have an x-intercept of positive 2. Instead of negative 6, we have an x-intercept of positive 6. So to go back to find the x-intercepts, the opposite of the constants in the factors. And the vertical stretch, we saw that in example 2 where we had the 2. The vertical stretch is the a value at the front of the equation, or the front of the expression. So example 5 was the last example that we did in class. What we're going to do here is we're going to factor our function. We're going to write it in factored form. We're going to identify our x-intercepts, line of symmetry, vertex, y-intercept, and if there's any vertical stretch, and graph it ourselves. And then if you wanted, you can always check it with technology. I'm not going to take the time in this video to check with technology, but we could enter the equation in the calculator and see if our graph matches. Now when we have standard form, we know that x squared goes in the upper left and negative 8 is going to go in the bottom right. We also know that x times x is what gives us x squared. In our most recent factoring problems, we would take the a value times the c value. So our a value here is 1. 1 times negative 8 is negative 8. So we're looking for values that will multiply to equal negative 8 and will add to equal the negative 2 that we have in the middle. Students in class were quick to point out that it would be negative 4 and a positive 2. That would multiply to give us negative 8 and add to give us negative 2. So we have a negative 4x and we have a negative, or a positive 2x, excuse me. So to get negative 4x, we take x times negative 4. To get a positive 2x, we take x times a positive 2. So our factored form is f of x equals x plus 2 times x minus 4. Now that we have it factored, we can identify the x-intercepts, which will be the opposite of the positive 2 and the negative 4. So one x-intercept is negative 2, 0. The other x-intercept is positive 4, 0. To find the line of symmetry, add the x-intercepts together. So negative 2 plus 4 divided by 2. That's 2 divided by 2 is 1. So our line of symmetry is x equals 1. The vertex will have an x value of 1. To find the y value, I'm going to use my factored form to do it. I need to substitute the 1 for x, so 1 plus 2 times 1 minus 4. That's going to be 3 times negative 3, which is negative 9. So our vertex is at the point 1, negative 9. For the y-intercept, we know that the y-intercept has a x value of 0. So to find the y value of the y-intercept, substitute 0 in for x. We have 0 plus 2, 0 minus 4. So we have 2 times negative 4 is negative 8. And for the vertical stretch, I can look at my original equation, and it was a 1x squared. So we can say that there isn't any, or that the vertical stretch is none in this case. So let's plot the points for our graph, starting with the x-intercepts. Negative 2, 0, positive 4, 0. The line of symmetry we identified as being at x equals 1. We identified the vertex as being located at 1, negative 9. We identified the y-intercept as being 0, negative 8, and because parabolas are symmetrical, I know I will have one at 2, negative 8, a point as well, that is. Using those points, we can graph our parabola. And there we have it. I will pick up with the next screen in the next video.